Hi everyone, it's me Diane from Tutopiya. We are back with a new video. Today we will be learning about distance and velocity. Without further ado, let's get right into the lesson.
Hi everyone, this is Nusra from Tutopiya. Today in this video, we are going to discuss a physics topic, especially the distance time graph, which we shortly call saying dt graph, and the velocity time graph, which we call vt graph. And the distance time graph is the graph that shows the relationship between the distance and the time of a movement. When an object is moving, the dt graph shows the distance moved by the object related with the time. So the first thing that we have to do when we are plotting a dt graph is labeling the axis, and normally in x-axis we do label the time, and in the y-axis we do label the distance. So here it will be meters and here it will be the seconds. That is the unit. And gradient of the dt graph. So we know the slope or the gradient of the dt graph can be found out using the equation. We know normally how to find out the gradient. This is y2 minus y1 over x2 minus x1. So in the gradient, let's, for an example, if we are taking this graph and if we are trying to find the gradient, we have to pick 2 points and we have to get the x and the y values and in the each point. So let's say this is 2 and 6, the seconds, the time in seconds, and the distance here, let's say it is 2 and 10. So that 10 minus 2 over 6 minus 2, which will be 8 over 4. So in short, it's 2. And how about the unit? So these values are from the distance, that is meter. These values are from the time, that is second. So for the gradient, we do have the unit meter per second. And we know meter per second is the unit of the speed or the velocity. So meter per second, if meter per second is the unit of the velocity, and if it is the unit of the gradient of dt graph, we can conclude saying the gradient or the slope of the dt graph gives us the speed. So the speed can be calculated, the velocity can be calculated using the slope of the dt graph. Now let's look at the dt graph that we can draw for an object which is not moving. So for a stationary object, the first thing that we have to remember is labeling. Here it is distance, and let's say it's in meters, and it is time, so let's say it's in seconds. Now if the object is not moving, we are going to have a parallel line to the x-axis. It's because our movement, if there is no movement, the distance cannot be changed. The distance has to be stationary. So here, let's say for an example, if it is 10 meter, even though the time is passing, the distance does not travel, so that we can say the object is not moving. So a parallel path to the x-axis in the dt graph tells us the object is not moving. And the movement with a uniform velocity. So we said at the beginning, by the beginning of the topic, we said in a dt graph, the gradient is giving us the velocity. If the gradient is giving us the velocity, and in order to get the uniform velocity, the plot should give us the uniform gradient. So for the uniform velocity, the plot will be looking like this in a dt graph, where the gradient at all the points are the same. The gradient has to be the same throughout the movement. If the gradient is the same, the velocity is the same, so that we will have the uniform velocity. And movement with a uniform velocity returning to start, that is just the opposite direction. So we know uniform velocity, the gradient has to be the same throughout the journey. Let's say this is distance and this is time graph. And over here, it has to be decreased down like this in order to get the object moving in the opposite direction with the uniform velocity, that is with the uniform gradient. And getting faster, that is acceleration. How are we going to get the accelerating dt graph? Acceleration is speeding up, that is the speed has to increase each second. So in that case, if the velocity is calculated by the gradient, if the gradient has to increase each minute, each unit, each second or each minute, the gradient has to increase in order to be an acceleration movement. So a plot like this, a curve like this will be giving us increasing gradient at each point. So over here, let's say the gradient is 2, over here it will be 5, then 8, then 10. So when the gradient is increasing, the speed is increasing, so that the movement is acceleration movement. Getting slower, the opposite of getting fast, that is acceleration. So this is deceleration. And when it is deceleration, the gradient has to decrease each unit of time. So let's say the deceleration should be, plot should be a plot where the gradient is being decreasing each minute. So when the curve is moving towards the x-axis, the gradient is decreasing. And this plot is giving us, this plot in the dt graph is giving us the deceleration, that is slowing down. We are now moving to the velocity time graph. A velocity time graph shows the speed and the direction of an object that has been traveled by this object over a specific period of time. And in the VT graph, we have velocity in the y-axis and time in the x-axis. Sometimes it is also called the speed time graph, because speed and velocity are the same, only the difference that we have is the velocity is the vector quantity, whereas the speed is a scalar quantity. So velocity has a direction, whereas speed does not have direction. Sometimes we do also call the velocity time graph saying speed time graph. And when it comes to the velocity time graph, we have to remember two things. Like in the dt graph, the gradient in the dt graph was giving us the velocity. The gradient in the dt graph was giving us the velocity. Let's have a look about the gradient of the vt graph. So in the vt graph, the gradient is y2 minus y1 over x2 minus x1. But here is time. Our x-axis is time. That's right. But our y-axis is not distance, but velocity. So gradient is, in short, velocity being divided by time. And we know v by t is equal to acceleration. We are familiar with this formula, so that when we are calculating the gradient of the vt graph, we are going to end up having is the acceleration. But in addition to the dt graph, we have one more thing to be known in the velocity time graph, that is the area under the graph. So when we have a plot like this, if we are calculating the area under this graph, obviously this area is going to be equal to the distance traveled by the object. Because here this is a rectangle and the area of the rectangle is length into width. Here it is velocity into time, because this amount is the velocity and this is time. So v by t is distance. It's because by the formula we know velocity is distance being divided by time, so that v into t is distance. And in case if our plot is looking like this, where we are going to have a triangle, if we are getting the area under the graph, This will be a triangle, and when it is a triangle, we have to find the area of the triangle in order to get the distance traveled by the particular object. Uniform velocity. How are we going to get the uniform velocity graph? The first thing that we have to remember is our y-axis, which is velocity, our x-axis, which is time. And when it is uniform velocity, what we have to know is the velocity is not changing over the time. So it has to be a parallel line to the x-axis, where the time is keeping on increasing, but the speed is not changing. So uniform velocity, if the movement is having the uniform velocity, that can be drawn like this in the VT graph, but in the DT graph, we have to remember this is stationary. This is for no movement because the distance is not changing. But this kind of a plot in the VT graph tells us it is the uniform velocity. And uniform acceleration. So in the DT graph, our acceleration was that is speeding up. So we had a curve-like graph. This is DT graph, and this was our acceleration in the DT graph. But in the VT graph, we know the acceleration is gained by the gradient. So since this is uniform acceleration, the gradient has to be uniform. The gradient has to be the same. So we will be having a graph like this for the uniform acceleration in the VT graph. And uniform deceleration. Uniform deceleration is nothing but having the VT graph with a plot that has the uniform gradient throughout. So V, meter per second, T, that is time second, and it has to be uniform deceleration. If it is uniform, the gradient has to be the same, but at this time it has to be in the opposite direction, since this is deceleration, so that we will be having graph like this. Now, let's get the VT graph and DT graph summarized. First, if the DT graph is this, this is the DT graph that we are having, where we are having an object moving like this, and then this, and then this. So what can I tell about the first region is the object is having a uniform gradient, so that the object is moving with a uniform velocity. At the second phase, the object is not moving. And in the third phase, the object is moving with a uniform velocity but in the opposite direction. Now, if it is the VT graph, let's say everything is same, but this time we are having the VT graph. This time the region 1, it is for the acceleration, and especially if the gradient is the same throughout the journey, it is uniform acceleration. And over here, the second phase, the second region, the object is having the constant velocity, the uniform velocity, and the third one is still the same gradient, so uniform deceleration, but in the opposite direction. So we do use the word deceleration when it comes in the opposite direction. And if this is the VT graph, in case if the question is to find the velocity travel or the velocity of the object at the 5th second, we can directly read the velocity at the 5th second. If the question is to find the acceleration at the 5th second, we can go for the gradient. And if the question is to find the distance traveled within the first 5 seconds, we have to get the area of this triangle. And we know the formula for the area of the triangle, which is half into base into height, so that instead of the base, this time we can get the time, which is 5. And if the amount of the velocity is given, that can be considered to be the height. So this is how we do go with the calculations in DT graph and VT graph. The final summary of this topic: in the DT graph, we will be concerned about the slope, that is the gradient, and the slope will be d2 minus d1 over t2 minus t1. And we know d over t, the change in distance over the change in time, is simply the velocity. So the gradient, the slope of the DT graph is going to give us the velocity. But in the VT graph, the gradient will be v2 minus v1 over t2 minus t1, so that we are having the change in the velocity and divided by change with time. So v by t is acceleration, then the velocity in the velocity time graph, the gradient gives us the acceleration, whereas the area under the graph gives us the distance. So another important thing that we have to remember in VT graph is, when it comes to the area under the graph, it can be a rectangle or a square when the graph is looking like this. That is uniform velocity. That is uniform velocity. Or else it can be a triangle like this. If the plot is this, it has to be a triangle. Oh, if the graph is looking like this, it has to be a trapezium's area. So it depends, the polygons or the area, the formula that we have to use to find the area depends on the polygon that we are going to get when we are finding the area under the graph. Saying this, we are winding up with this video, and let's meet in another video with a fresh concept. Thank you, everyone.
Thank you for watching this video. If you have not subscribed yet, make sure to do so and turn the post notification bell on to be notified whenever we upload a new video. Thank you for watching and have a great day. Bye.